Today I shall discuss formalism, like formula in chemistry or formula in mathematics, but for the structure of dispersed system. And this is why it is called DSF, dispersed system formalism. I shall explain that this formalism is useful in order to understand really the microstructure of some colloidal system, for example, emulsions, foams, gels, suspension, and so on. Sometimes these systems are not pure. For example, imagine that you whip an egg white and you add some oil. You would get a dispersion of oil droplets and air bubble in the aqueous phase, which means that it's a foam, certainly, but it's also an emulsion. We could say foamy emulsion or emulsimide foam, but indeed we need a clear way to distinguish between the two. Now, when you have such formalism, you can use it to produce new formula, which means that you can make a new system that you did not imagine before. And finally, the DSF is very useful for scientific research, in particular in molecular gastronomy. So let's go. We start from food, but it could be drug, it could be cosmetics, it could be paintings, it could be varnishes. We want to study some physical systems. And of course, food will be used because it is the topic of molecular gastronomy, but it's the same story for all the other systems, and it is what all these studies could be called formulation. Indeed, it's not completely right, because formulation you need to formulate. But anyway, it's a tool that's clearly useful for formulation. So let's start from food. This is food. Indeed, there is a small difference between food and dishes. It's a dish, and by the way, it's a dish by the three-star chef Pierre Gagnère, having restaurants in most capital cities of the world. And this food is clearly made out of parts. So we see them at macroscopic level, and we see with our eyes at this scale, which is the size of the plate, let's say 20 centimeters. We see an organization with parts. So there is clearly a layer of sauce on top, then the creamy sphere. Underneath you have the yellow one, and below you have the leaves and the sauce again. So you see, we have 1, 2, 3, 4, 5 parts. This is the macroscopic organization, and in this case, it's only one top of the other. Okay. Now, if we consider one of these parts, and we take a small sample and we look at the microscope, we will be able to see a microscopic organization. Indeed, what we see here, it's a sauce mayonnaise at the beginning of making, and we see the white circles or discs are the oil droplets, and we see three dark shapes, spherical as well, which are 3 air bubbles. But indeed, it's an artifact for the preparation of the microscopy. So here we see that this emulsion, it's an emulsion, is made of oil droplets dispersed into water. At the bottom, I put the size of the structures. The oil droplets, the biggest, are 0.1 millimeter, and let's say that the radius can be divided by 100. So now we have a microscopic organization, and it would be a different one for the other macroscopic part of the first slide. Now, if we take this structure of the microscopic organization, one of them, we can see more deeply with a nanoscope, let's say, and we would see the nanoscopic organization. So you see the scale here, the bar is 50 nanometers, billions of meter, and these are casein micelles that you can find in milk. You see there is an organization as well, and indeed if we had a huge microscope, then we would be able to see the molecules. But sometimes the molecular organization that we would see can be distinguished by its effect at macroscopic level. This is the case. In this case, I have added some tin salts to the raspberries on the left, and they turn blue immediately because there is a complexation between the anthocyanins and the tin ions. So you see organization at any scale. And now we come to the main idea of formalism. Here is a treaty of logic by Goblet, and we don't need to read everything, and it's in French, by the way. So what Goblet says, it's notation or formula can lead to discovery. This is the most important idea from this text, and indeed it was used by Lavoisier, Antoine Laurent de Lavoisier, the founder of modern chemistry, because he used quantitative information instead of having only reactions that you could see precipitation, change of color, and so on. And indeed, the formalism of chemistry that we use today was built by Lavoisier in 1782. He wrote in the text, I built some formula. It's not exactly mathematics, algebra, but it's a different principle, but we could start with that, and it makes thinking easier. This is a very important sentence at the end. This formula make us more at ease to see, to understand the systems. So this is exactly the same for the DSF formalism. So we will have time to discuss the building of this formalism. It is based on operators first, then dimensions, not size but dimensions, mathematical dimensions, and faces. I shall discuss the three in the reverse order. The faces, it's in food, you have sometimes some air bubbles, for example, in whipped egg white. This is a gas, okay. It could be helium, it could be dinitrogen, it could be something else, but a gas is a gas, letter G. Now, we have often aqueous solutions, for example, wine, orange juice, meat stock. They are all made primarily of water, so it's an aqueous solution. The physical chemistry calls that aqueous solution, and we put the letter W like water. Okay. Now, O for oil. Oil means any fat that is liquid. You have to know that, and you know, by the way, that when you put olive oil in the fridge, when it's very cold, there is a precipitation of part of the fat and make crystals. Which means that for oil at room temperature, it is all oil, letter O, but if we cool it, we could get a solid. And this is the next line, solids. It can be starch granules, it can be, generally it is divided, okay? For the dimension, I told you that it is not the size, it is a mathematical dimension. For example, a dot, a line, a sheet, or a block. Let's have an example. A seed of rice would be a dot if we consider the size of reference as 20 centimeters. It can be defined very precisely, but let's say very briefly that the size of rice is more than one order of magnitude smaller than the size of a plate. For lines, you could think of spaghettis, sheet, for example, a sheet of salad, and block, it's a piece of meat, of fish, or something. Now for operators, we'll go into details with picture explaining that better now. But let's see that we have 5. Random dispersion, coexistence, inclusion, superposition, intermixing. So let's go. So we consider first the microscopy of the surface of chocolate. We see at this scale some fat crystals, which mean solids. It's fat, it is solid, because you know that chocolate more or less begins melting at 34 and finishes at 40. It's not exactly that, but you can keep this idea. And now part of the chocolate is melted, and it is inside the chocolate. So this demonstrates that the chocolate at this temperature is a gel formally, because you have a liquid inside a solid. Okay. Of course, the structure, the microstructure, would change with temperature. If you eat at 50 Celsius degree, the chocolate will be melted and it will be pure oil, the letter O, remember. But now we need O and solid and S. Okay. Now, is it an emulsion? No, because an emulsion means a dispersion of a liquid into another liquid. It can be water into oil, oil into water, water into water, oil into oil, and so on. But we need 2 liquids. And in the case of chocolate, we add a solid. So this is not an emulsion. Now, is it a gel? And I told you that it was a gel because we have a liquid inside a solid. So really, the chocolate at room temperature, 20, let's say, is a gel. Okay? Now, let's look at this picture. This is the cream on top of your espresso coffee. Or espresso, they say in Italy. Now, it is said that it is a cream. But cream is made from milk with a lot of fat droplets. And the fat creams, which means that it moves upward to make a concentrated emulsion. And indeed, the question here is that there is no oil droplets. What you see is the microscopy of the cream of the espresso coffee, and you see indeed it is a foam, because a foam means air bubble dispersed into liquid, as it is well recognized by UPAC. UPAC, you see the 3 slides, one of emulsion, one on gel, and the third one of foam. UPAC is the International Union of Pure and Applied Chemistry, and it defines in the Gold Book, or the Compendium of Chemical Terminology, defines the way that we use in chemistry. So it's an international recognition, so we cannot invent anything. We have to come back to UPAC Compendium each time we use a scientific term. Now, let's look at a plant tissue. For example, this is a shallot. What do we see? We see a liquid, the white part, inside a solid. And indeed, the shallot is made of probably 80% water inside the solid shallot. The shallot itself does not flow, but it is made of a high quantity, high proportion of liquid. So indeed, formally, it is a gel. So all plant tissues are gels, and by the way, it could be the same with meat. Now, let's stay for 1 second on plant tissue. This is a microscopic picture of a potato. We distinguish hardly the limit of the cells, because the potato, the tuber, is made of cells that are aggregated, let's say. And inside the cell, you have water, plus these teeny solids, which are starch granules. The blue color is due to a colorant, that is iodine, that was added to see them better. But you see, we have a certain number of starch granules inside any cell. So in this case, the system is more complex than the previous one with shallot, because indeed we have some solids into water, and this is named a suspension, and this suspension is dispersed into the gel. So now we begin to see that we need a tool for describing this kind of system. Egg yolks, now it depends on the scale. This is what I want to demonstrate with this picture. This picture is a huge magnification of egg yolk, and we begin to see the granules that are dispersed into a plasma. A granule is a solid, a small solid. It can be a soft solid, but let's say that it is a solid. And a plasma means more or less an aqueous solution with protein. So indeed, the egg yolk is made of 50% water, 15% protein, and 35% fat. So at this scale, we see a suspension. But now if we look at the bigger scale, for example, when we make a custard, adding some sugar and whipping, you see, adding the sugar, we see the sugar crystals. But at this scale, we don't see the granules, which means that in order to make a formula, we need first to define the scale at which we want to describe the system. Okay. And in this system, it would be solids, solid particles, dispersed into a liquid. And this is called the suspension. Of course, there are some air bubbles, but there are artifacts. Now, let's whip the former system. When we make a custard, we first add sugar to egg yolk, then we whip. And when we whip, it turns white. Why? Because you introduce a lot of air bubbles, and at the same time, the sugar crystal dissolve into the water of egg yolk. So now it turns white as whipped egg white is white because of the reflection of the white light of the day on the droplets. The size of the droplets is again like for mayonnaise before, smaller than 0.1 millimeter. Now we cook the former system. What do we see? We see a coagulation. Indeed, it is the same magnification as before, but we see that the proteins have coagulated. They have made some curdles. So again, now it's a suspension. And we have to come now to gels because the gels are the most important system, I would say. I told you that it was a gel, a plant tissue. But now, if you consider meat also is a gel because look, the human body is made of 70% water, 20% proteins, and 10% fat, more or less. And indeed, if you look at the meat in your arm, for example, and you cut it transversally, this is what you would see. You have fibers, long fibers, that are grouped into bundles, and the bundles are grouped into super bundles in red in this picture. The colors are not the right one. The colors are due to colorants. But you see, each fiber contains a lot of water. And overall, there is a structure. So you see, it's again water into a solid, and it is a gel. Now, gelatin gel, which is a very common gel. When you say gel, they think generally of jam or gelatin gels. This is electronic microscopy, and the size of structure is not given, but they are much, much, much smaller. Let's say that one small, the diameter of one of these holes would be 10 to the minus 7 or 8 meters. But indeed, you have the gelatin molecules making a network in which water is trapped, because a gelatin gel does not flow. So gelatin gel is a solid, it does not flow, but indeed it is made, it contains a lot of water. And this is a gel. And you see that it is not the same gel as before. Now, the cooked egg white is also a gel. The cooked egg yolk is also a gel. By the way, this is a very poor hard-boiled egg because of the many defects. For example, the yolk is not at the center. There is an awful green color around the yolk, which means that there is probably a very bad sulfur odor. Anyway, but anyway, it's a gel. But now I come back to gelatin. You see, these are two gels of gelatin. One is on the left is 25% of gelatin with water, and the one of the right is 5%. Some blue colorant has been added at the beginning of the experiment on top of the gel, and with time there is some diffusion of the colorant inside the gel, and this diffusion is faster when the gel is not too strong, as would say the cooks. But you see, some diffusion is possible. On the contrary, in the shallot tissue, no diffusion was possible. So now we have the question. We have here two gels. They are more, by the way, but there is only one word, and it's not fair. We need different words to describe different objects. Imagine that we have on the left a cat and on the right a dog. It's not enough to say that it is, let's imagine, a cag. No, we need two different words, cat and dog. So we need the same for gels. When I was a student at the École supérieure de physique et chimie de Paris some time ago, this is a table that I was shown by our professors in colloidal physics. By the way, it's quite wrong, but it's useful. We should not keep it because we need to keep the UPAC, Gold Book on Definitions. But anyway, it's true that when you put a gas into a gas, it's not a dispersed system, it's a gas. When you put a gas into a liquid, it is clear that you make a foam. A gas into a solid, it is called a solid foam. A liquid into a gas, it's like when you make some sputters and then you have a liquid aerosol. A liquid into a liquid, sometime when the two liquids are immiscible, it makes an emulsion. A liquid into a solid, it's a gel, clearly. Now, the solid aerosol, a solid into a gas, for example, the smoke of the cigarette is made out of particles. A solid into a liquid is a suspension. Solid particles dispersed into liquid, and solid into a solid, it can be a solid suspension. But now, you see, this table is not enough because how would you describe this system, which is quite usual, quite common? With the words that we have seen, it is not possible. So we need something more. And this is why, in 2001, I proposed DSF at the World Congress of Emulsions in Paris. I will not repeat the operators, the dimensions, the faces. There are articles on chapters of book about that. But now we have to come back to this picture. How would you use the formalism to make the formula of this system? Remember that we have to define first a scale. And at any scale, there will be perhaps different formula. Now, because life is complex, we need to make it simple. So I introduce now the idea that we have to use when we make this kind of analysis of finding a formula for a system. This is the spectrum of coffee, with nuclear magnetic resonance. And you see, coffee is a complex solution, but if you look from far away, what you see is one signal, and it is water. And it's true, coffee is made primarily out of water. So this is the first order of magnitude. Now we are going to multiply this by 10, which means that we get closer. And when we multiply by 10, this is what we see. You see the water signal is so big that we don't see any longer, but we know that it is water. And now we see 1, 2, 3, 4, 5 signals. And 5 signals, this is very easy to analyze. So you see, when we analyze the first order of the first order, which means the second order, it becomes much more easy. By the way, here at 0, the abscissa 0, it is ppm. This is, I will not explain, but this is the frequency. At 0, you have one signal, and the signal is a reference that we put with coffee in order to fix the picture, let's say. So indeed, there are only 1, 2, 3 signals to analyze, which is easy. Now, when this will be done, we will multiply by 10 again, and this is the picture that you are going to see. But you see now the noise begins to appear, and we will have to stop after this analysis, because there will be the noise, and the noise is nonsense very often. So now we have the idea that we are going to apply. When you look at mayonnaise, for sure there are 3 air bubbles, but I told you that there are artifacts, and indeed their number compared to the number of oil droplets is a teeny fraction, which means that we should not focus on the air bubble, and we have to recognize that mayonnaise sauce is an emulsion, O/W, oil dispersed into water. Of course, the first line is giving the scale, and between quotes at the end of the formula, you have the size of the droplet. If you want to add them, it is not compulsory. So you see, it is very simple. Oil, O/W. Now, if we use the same system, we can describe very easily the potato at this scale. You have solids dispersed into water, S1/W, and these cells are dispersed into the solid of potato, which is solid 2. And you see, we don't need to get a name. We have a formula with 3 letters plus some signs. Of course, when you make such a formalism, you can add a lot of information about quantity, scales, kinetic information, and so on. You can make equations describing the evolution of system, but I want to avoid the discussion of this because it's not the core of the formalism. I want to come to the second aspect, which are the dimensions. I told you that there are dimensions 0, 1, 2, 3. You could use fractals as well, but let's stay with 0, 1, 2, 3. Now, we are mixing the first description with faces and the second with dimension. And here I'm showing 3 kind of quite complex objects with the full description with dimensions and faces. But let's come to some pictures that we have seen already. You see, at this macroscopic scale, the number of the formula is not very long. I will not into detail. I would prefer to analyze better this one. So you see, you have O, oil droplets. They are dimension 0 because they are smaller than the size of the picture, let's say. And they are dispersed into water, and water is dimension 3 because this is the continuous phase. Okay, so Kazan micelles, you could describe them this way. The molecular structure as well. And now I want to come back to gels. So here you see this is water, dimension 0, randomly dispersed into solid D3. Okay. But what about using the same formula to make it differently? So now it's very easy. We need to make some water droplets, let's say, dispersed into a solid. And this one was served in a restaurant. It is my invention that I called conglomel a long time ago. And they are alginate pearls, like salmon eggs, let's say, but artificial, fully artificial, and they are glued together with gelatin. Now, we come to potato and look at the formula of potato. By the way, it was not difficult to establish, but it can be used differently. The same with meat. You know, meat, in this case, we have fibers, which is dimension 1, by the way. And we could easily keep the same formula and make it artificial. Sometimes the gel are not recognized as gel. I told you about chocolate, but the scientific community does not recognize always that it is a gel, and it is a gel. Now, at some temperatures, there is a funny organization because the solid phase is continuous, but also the liquid phase. And in particular, one can study the chocolate at certain temperature using mercury porosimetry, which means that we push mercury, which is a liquid metal, through the chocolate network in order to recover the liquid fat. And this is a demonstration that it is a gel. Now we see the dimension, the formula for a gelatin gel. We have a continuous solid, a continuous liquid. So this is why it is not a random dispersion, a slash, but an X. Sometimes the gels are more complex. For example, this is the plant tissue with one of the conducting channel, xylem, phloem, and you see the formula can recognize the presence of this. Of course, we could make an artificial meat. This is what I call the fibré. And now, clearly, we can distinguish the gel. This was the purpose of the dispersed system formalism at the beginning. Of course, we can have many formula. The number of formula is infinite. Here, I wrote the formula for an arbitrary system, but what I did probably in 2002 or 2003 was to use a random generator in my computer to produce an easy formula, and this was the formula, and to make it into a dish. And the dish was called a Faraday. In this case, it was a Faraday of lobster. So it was the first dish that was made from a formula. Another application, and this is a metaphor because here you have the French classical sauces. There are 451 sauces from certain books that are given in some publication. But anyway, it could be the products from a cosmetic company instead. It could be a category of shampoo, or it could be any formulated products. But let's stay with the sauces. What we are looking is for laws and structure. So, you know, the list before was a mess, and we need to organize to understand something. So, indeed, we know that some sauces are solutions, emulsions, and so on. So, we see clearly that the DSF is useful. And this is what the work that was done a long time ago, to take all the sauces, to make them, to look under the microscope and to establish the formula. And the result is there. There are only 23 categories, physical categories of sauces. And so they are given in order of complexity in this slide. But it's funny to recognize that some easy formula are missing. So why not make them? And indeed, we did it, and it is very easy. Why only 23 categories? So here I display the number of physical categories of sauces in function of time in the history of cooking. The blue dot on the left is for the De Re Coquinaria by Apicius. It is a collective book, and indeed it's not only at minus 400. The publication was spread over centuries. But anyway, we want French classical sauces, so it's on the right. And you see the number of categories have increased. Now it is infinite because we can make what we want. Now, the big issue about that, or the big scientific question is given in this picture. We know that we have a large number of formula. Out of this formula, we can make physical systems, and these physical systems will have chemical and physical properties. Can we predict the properties from the formula. I will not have time in my life to study this question, but I'm sure that it is a very important one for the formulation industry. By the way, as we discuss the practice, this is what we made very briefly after my discovery of the DSF. With a friend, Volker Hessel, in Mainz in Germany, we used microreactors, and it was very fast to use a formula and to make a system, a sauce. Okay. Later on, this equipment was produced with a computer driving the pumps, and it was used in the technological fair in Frankfurt, in Germany. We were playing with orange juice, vodka, olive oil, Cointreau, and so on, Curaçao, and the visitors were typing their formula and getting cocktails. Now, this is the prototype of a machine that could be in kitchens. At the core, you have microreactors, and they are in line or in parallel, and you see the number of possibilities is more than 500 billion possibilities with different consistencies, so very efficient. Now, what is probably better for me is to use the DSF for scientific research. I wanted to know how many gels can exist, because we have seen some of them, and of course there are simple gels, for example gelatin, but you imagine that you would put some oil into water before gelling with gelatin, you would have a more complex gel, and imagine that you would add as well air bubbles, it would be an aerated emulsified gel. So you see there are classes of gels, and on the left you have a small computer program in order to know how many gels we can make. And indeed, the answer is for simple gels, there are 16 only. So this is interesting, I would say, because now that we have the formula, we can recognize them more easily. And now, how many gels of class 2, more complex? We have the same kind of program, computer program, and here are the results. About 1,500. So they are here, and here. That's all. Now we could move to class 3, class 4, and so on. But you see, there is a huge number of possibilities before moving to more complexity. The same for suspension. Suspension, the definition is given because we did not give it before. And indeed, the same kind of program for the same kind of results. These are the class 1 suspension. And for suspension of class 2, we have only 158. So you see, this is very efficient for description, for innovation, for research, and okay. Now, something funny. It's practice, it's not theory. For some food, when you put the food in your mouth, the flavor is appearing very fast on the left. And for some other food, the flavor is appearing slower. But could we make a gel we put in our mouth and we have one flavor that would disappear, another one that would disappear, a third one, and so on. And the answer is yes. We did it here. It was in Aarhus, in Denmark. In the morning, I lectured for chefs and PhD scientists, and in the afternoon, they had a practical session, and this was one of the results having this kind of properties. Now, this is described in the Handbook of Molecular Gastronomy, a big book that you can find easily, and I finish by saying that chemistry is really wonderful. Indeed, I was focusing more on physics than on for chemistry, but this is the same kind of activity. On this picture, we see Hermes at the right, speaking to Bacchus, Hermes, the god of chemistry, speaking to Bacchus, the god of good food. And I'm giving my email so that you can use it if you have any question. I did not put any reference, because it would make the slide more cumbersome, but we'll be happy to give them to you if you need them.